Okay, now for our second part here. In our first part, we went ahead and figured out what was the volume of the oxygen given the conditions that we had when we ran that reaction of breaking up that mercury 2 oxide. So now we're at the same idea, same reaction, okay? Same conditions, except the differences are we're going to have 400 degrees Celsius and 740 torricelli. Okay, well, how do we go about doing that? Well, we're going to need to do some conversions. I'd just go stick with the conversions first. I'll feel a lot better about it. I know that my temperature is equal to 400 Celsius, but I need to change it to Kelvin. So to change it to Kelvin, I need to add 273.15, and that's going to give me 673.15 Kelvin. So that's my temperature that I am going to be working with. Okay, now for my pressure, well, we want to change that to ATM, and the reason why we want to do that is because of our R constant, because that has the value, the unit of atmosphere. Okay, so that would be kind of an important thing that we have there. So pressure, we know 740, okay, torr over, well, we don't know what the atmosphere is. Okay, but we end up getting 760 torr at the beach. Okay, whoops. Go ahead and erase that. So we're going to get 760 torr, again, at the beach. And we know that's going to be over 1 ATM, because that's what we know at the beach. All right, so our pressure now being converted, we know that it's going to be 740 is equal to 760 times X. Okay, so we're going to go ahead and we're going to say that pressure is equal to 0.97 atmosphere. Okay, so we're good on that. So far, we've got our temperature. Whoops. So far, we have our temperature. We have now figured out our pressure, so we're good for that. Likes to do that for some reason. Okay, so extend the page, extend the page. Okay, so we've got that so far. Now, we're going to go and take the number of moles of oxygen from our previous problem, okay? And that, ladies and gentlemen, is 0.0095 moles, and that is our N, okay? We have our T, all right, we have our T is equal to 673.15 Kelvin. We know that. And our pressure is equal to 0.97 atmosphere. And R, well, R is a constant. We know that, 0.083. R is your friend. Ladies and gentlemen, this is it. We have our pieces. Now we got to go for the next thing. We need to have the formula. Well, what is the formula? It's the ideal gas law. That's what we're looking at here. So the ideal PV equals nRT. That's our ideal gas law. In this case here, we're interested in the new volume. That's what they're asking us for, because they changed the conditions, but they still want to know what is the volume of the oxygen produced in this reaction. Okay, so we got to get volume by itself. This is where we'll say, I'm drawing the arrow, and I'm going to say V is equal to nRT over P. So that's the formula we're going to use as we're winding this down, because we are in fact winding this down, ladies and gentlemen. So here we go. We know that it's going to be 0.0095, okay, times 0.083 times 673.15, okay, and we're going to have all that over 0.97. I'm going to turn around and say, well, this looks like a bunch of numbers fit in. Well, let's take a look at this. This is our, whoops, this is our N, this is our R, here is our T, and here is our P. So what I did, I showed you what parts, what numbers belong to what part of this equation, okay? So we're going to go ahead, we're going to multiply that all out, and you end up getting 0.531, depending how you rounded it, over 0.97. And then that's going to equal our final answer, ladies and gentlemen, of 0.547 liters. And that's it, ladies and gentlemen. This concludes the video for this particular problem dealing with gas and stoichiometry. Thanks for watching.